Thanks, Ross, for the nice introduction, and thanks to IEEE BTS for giving us an opportunity to talk about our current paper. It's great to see being a very young RF engineer talking in a platform where a lot of expertise to take. So the title of our paper is High Power Directional Waveguide UHF Balanced Combiner Design for Efficient RF Filtering and Combining. I know it's a long title, but essentially what we are trying to present today is we have come up with a Generation 2 Directional Waveguide Balanced Combiner, and we're going to talk about what are the improvements we did on Generation 1 and some of the results. So just a bit of outline of today's presentation. Definitely we're going to talk about what was the motivation of coming with this project and what are the objectives or outcomes we were expecting initially, and definitely what were the Generation 1 Directional Waveguide Combiner. And on top of that, what are the improvements or innovation we did on Generation 2. And I'm going to go a bit design process for 7-pole dual cross-coupling combiner, and in context of ATSC 3.0 as well as VPT, which is variable polarization technology, how this particular product suits, okay? And finally, a bit of conclusion. So what was the motivation again? So as we know, spectrum repack is happening. There is a greater or increased volumes coming in, and we need to shorten the lead time for delivery. So we wanted to revisit the manufacturability and the design of these waveguides. And also for ATSC 3.0, the power handling is needed much more than ATSC 1. So we wanted to reinvestigate the power handling capacity for our combiners. And also we wanted to take the advantage of the shrinking of the frequency band and make some more improvements in terms of standardization of our components, and finally reduce the cost. So the objectives or the outcomes that we were expecting, and the first two things are the most important, I would say, is how we can improve the power rating. And essentially we could double the power rating, keeping the same footprint or same size of the combiners. And also we essentially, we have the manufacturing lead time, which is one of the key things that we looked for. And definitely we did standardize the model, so you can have greater stock of the items and essentially cut down the lead time for production. And essentially what we have now is kind of a plug-and-play module where during different stages of repack, you can essentially have different channel combinations in a combiner chain, and before you reach to your final stage of ATSC 3.0 launch out. And we had natural convection for these combiners, and we still kept the natural convection, and we don't need any air forced or any water cooling. Now, just a bit of background about what are the other solutions in terms of fixed tune waveguide combiner. Definitely this one is the balanced combiner module, which is very popular, has been used for a long time, but definitely these are pretty big and a large footprint area. Essentially you have to hang it from a ceiling, and also has a longer lead time, and cost is a bit high. Manifold combiner, as our previous speaker talked about, they're pretty cost efficient, easy to install, but definitely there are some cons in terms of limitation of how many number of channels you can be combined. Particularly when you have put it in a field, it sometimes gets a bit difficulty to add a channel. And also what we are looking for our combiner is how we can add adjacent channels, which is not possible in manifold combiners sometimes. So when we go to directional waveguide combiner or a fixed combiner chain, as you can see in this photo, essentially it has a very small and compact footprint area. As here, this is a wave. I'm just going to use my mouse here. So this is a wave wideband input to output channel where you can, so we call it the spine, and you can add any number of channels from the narrowband to the wideband. And also because it's very compact and it can have standardized module, you can take out any channels and add another channel if needed. So it can give you the flexibility of add or remove modules while you are doing different interim stages. And one of the things that we also looked into is if you want to add odd or even number of poles, you can do that. You're not restricted to use only even number of poles. And we use that feature to come up with a 7-pole dual cross-coupling filter and combiner, which we're going to talk about. Definitely there is a cons of there's height, which is greater than the folded combiners, but we have also worked on reducing the height. Okay, so just again for those who are not familiar about these particular combiner, so essentially this is a CIF combiner, okay? So this is a constant impedance filter combiner, and a CIF combiner has two 3 dB coupler back-to-back connected with a bandpass filter, which is tuned to the narrowband channel, and essentially the narrowband frequency adds to the wideband input at the operating band to the combined output. So what we have done in our directional waveguide combiners, starting from generation 1, is we have come up with a strategy or a technique to replace the 3 dB coupler, which is an extra component, by a certain coupling arrangement between the waveguide, rectangular waveguide, and the circular or cylindrical cavity. So what essentially is happening is when you have a TE101 waveform or TE101 waveform going through the rectangular waveguide and it goes to this particular slotting arrangement, it essentially produces two orthogonally polarized TE111 mode inside the cavity, which is also in 90-degree phase apart. And it does a job for the 3 dB coupler. And this makes the whole structure very compact. And on top of that, what we can use is, as you can see from the wideband input, the wideband output, we can use a multiple, wideband spine one after another and make it a chain as we need, according to our customer's need. So this essentially makes the whole structure very compact, and we have been employing that. And also, as we move on to our generation 1, as I said, so what was the issues with the generation 1, why we wanted to move into a generation 2? Essentially, in generation 1, we have been deploying it for about more than 20 years across the globe for these combined setups. They're pretty well, as I can see, they're the good features of compactness and really easy to install. But in terms of generation 1, what was happening is, essentially, we have a set of cavity heights which came from iterations or analytical method, and the most pressure was going onto the tuner of the production. So what tuner was doing, they were using these resonator screws, as you can see, to tune each of the cavities in a certain fashion to come up with the certain mask requirements, which was not an optimized technique because it wasn't a reliable technique in terms of timing. So I remember a couple of years back when I was given this task from my systems engineering manager on revisiting or reinvestigating this project. I asked, look, Luis, what you're actually looking for, okay? So the first thing Luis mentioned to me, my manager, is, Imran, if you can come up to me with a certain preset values, okay, for the tuning. So when I say preset values, what I essentially mean is, if you can tell me for each of the cavities, there are 4 tuning screws, yes, and also the coupling screws. So if you can tell me what are the preset values before the tuner actually starts tuning them in the production, that's going to essentially cut down the whole tuning time and make it much more reliable in terms of delivery. So I would say that was one of the main motivations we started this project, okay? So that's why we looked into the EM modeling of the whole structure and tried to understand whether we can essentially tune the whole structure. It's a bloody big structure, but tune it down in the software before a single copper is cut in the factory, okay? So that was the main thing that we did. And that's why I said, like, the electrical performance in terms of increasing the power handling capacity, also the insertion loss improvement, those were kind of a byproduct, because once you start looking into the EM fields which is moving around, and what you get an EM visibility. Then you start to understand where the critical areas, where there is a peak E field concentration or a current concentration, then you start nullifying them. And we have definitely our internal IPs of revisiting these structural parameters and try to improve the power capacity, whether it's a peak power or average power capacity. So that was the main motivation or main areas of improvement we look forward from generation 1, and definitely it reduced the cost and also the footprint area. So if I go to generation 2, what we essentially did, as I said, the main fundamental thing, what are the design approaches and outcome we actually came up with is, first of all, again, is we did a full EM solution simulation, and we looked into the critical shapes and we optimized them. So from the outside, you're going to essentially see looks like the same structure, but from the inside, we have done major, I said, renovations, if you want to say, or changes in the structure, which kept the same footprint area or the same size, but double the peak power rating. And I need to mention before, if you wanted to have the higher peak power rating, it essentially was you need to make the whole height double, but we are not offering that anymore because we can use it using the optimum position of each of the critical elements like tuning screws and coupling widths and also the coupling screws. Then we went into definitely it's as I said it's a complicated structure, but we come up with a method of simulation or making an efficient simulation technique to do the mesh optimization in HFSS and CST both, and we can really model the whole structure in a completely different channel and tune it pretty fast, less than 2 hours, I'd say. And now we also could accommodate any number of channel sequence in the chain. And there are other improvements we did for average power rating also. So because we looked into the structure and we found the coupling arrangements and coupling screws can be improved to improve the average power rating. And finally, as I said, the manufacturability and the quality control was improved. And to what point, and that's why it becomes very critical when you have a full EM visibility. So what we found, to have the optimum position of the screws, our cavity height has to be, the tolerance has to be improved. So we definitely had tolerance for each of the cavity heights about 2 millimeters, but we reduced it to 1 millimeter. It seems okay, so it's from 2 millimeter to 1 millimeter, but it essentially gave us a lot of opportunity to improve the power rating, because we could then ensure that the screws are not penetrating more, what can cause problem in terms of power rating. So those sort of things, little small things, made a lot of difference in here. So I'm just going to go through one of the variations that we are offering currently. So I won't go to details on the numbers, but essentially what we have here is a 4-pole and a 6-pole version. So it's a 4-pole without cross-coupling and a 6-pole with single cross-coupling. So these are the combiners for transmitters which does not have, a transmitter which has a masking filter out of it. So with mask filter, which has a mask filter from the transmitter, and 6-pole is for adjacent, and the 4-pole is for non-adjacent channel combining. And the 7-pole dual cross coupling is basically replacing the 8-pole dual cross coupling combiner, which we call the in-combine mask filtering. So you essentially, if you don't have a mask filtering out of the after the transmitter, this combiner can do the mask filtering for ATSC1 and ATSC 3.0. So if you look at the power narrowband input power ratings for 4-pole, it can go up to 120 kilowatts at the smallest channel, and also it has a good insertion loss and good roll-off. And definitely you have a question why we are offering a 7-pole dual cross coupling, not an 8-pole one. We had a detailed study on it, and we have looked into it, and we found, so when we are offering a 7-pole, we essentially are not compromising anything on selectivity or power handling. On top of that, the 7-pole essentially gives you as a better insertion loss. And also, the roll-off is the same as the 8-pole, both for ATSC 1.0 and 3.0 mask. And definitely, if you can have reduce one pole, you're reducing the height, which is also important, and also the cost. So this definitely is not possible for a folded type filter, but we could do in this combiner. So just gonna quickly go through the design process, what we employ in RFS. So basically, for these structures, for any new structure, what we do, we start working on a circuit model. So when we say a circuit model, we work on a circuit model which essentially resembles the structure in the 3D model. So the first we call it we make the circuit model, which we call a fine model. And then we move on to on the 3D simulator or 3D model creation. And in the 3D model, before going on to any iteration, what we do, we use the nominal values to come up with a certain structure. We call it the coarse model, which does not represent the actual or has the final scattering parameters that we need, but it has a pre-tuned state. For example, here the green response is from the coarse model, and the blue is from the fine model. So the whole idea for iteration, which is the step 3, is try to bring down the error function between the fine model, which is the circuit model, and the coarse model, which is the 3D model, and come to a stage where you can essentially reduce the error function between these two below an error threshold. So we have developed our in-house capability of extrapolating the circuit, we call it this equivalent circuit parameters from that 3D model or coarse model, and then calculate a delta function which essentially guides the user to change the structural parameters in the coarse model or the 3D model to bring the error function less than the threshold. Just an example how we achieve it in terms of scattering parameters. So as I showed before iteration or pre-iteration, so there is a large discrepancy between the two stages of the circuit model and the 3D model. But once you do first iteration, you essentially reduce the error function between the scattering matrix, and then as you go along, you improve it, and you come to a stage after maybe a couple of iterations or more iterations to a stage where you essentially reduce the gap, and it goes for the drafter to start drafting. And some of the results, this is a 7-pole dual cross-coupling combiner for channel 21 and 32. It was a challenging project we did for one of our customers. It has a high power requirement. On top of that, it was as an elevated station, and we successfully have done it. And there are some of the results. And one of the things that we did also, we actually for this channel 32 one, we essentially shoot it up to 80 kilowatts of transmitting power at the center frequency, and we looked into some thermal images, if there is any certain hotspot, but it worked beautifully in our site. So that was comprehensive testing had been done in our facility, and we are pretty confident about the capacity and the features. So now I just want to put some of the some slides on why or how it's relevant to ATSC 3.0 and VPT, which is variable polarization technology. First of all, when we move on to ATSC 3.0, there are high peak power requirements over ATSC 1.0, and essentially also in adjacent channels and semi-adjacent channels. So that's why we find these combiners are a good suitable solutions, and also it can improve the safety margin. And when you move on to ATSC 3.0, so we essentially don't need any modification in the overall system because it's already upgraded, or you want to say ATSC 3 ready. And for variable polarization technology, that's also one of the income technology that a lot of customers are taking. And we essentially want to have a controlled phase matching between the two chains, like plus 45 and minus 45. And we have shown in the current slides in an example where you can have much more control over each of the combiners to change the frequency, to change the phases of the two different combiner chains, plus and minus 45, to get different ratios of H and V. So that's also very useful, and definitely any combiner chain is not restricted for what number of poles you need to use. So I just wanted to give an example for a Dallas-Milton site, which is thanks to American Tower for giving us an opportunity to work on this project. And as we speak, it has been made in our production area. And it's a full around 200 kilowatt VPT system. And this is for the single chain. This is the specification. We have channel 18 and 19 coming from the previous wideband input. And we are offering three 4-pole CW combiners as we talked. And each of the combiners, one is for channel 21, 23, and 29. These are the power for single channel. And also we have, as I said, like we can accommodate any future channel that needs to be put later on for any interim stages. For example, at this stage, we have a blank spine where you can put any future channel like channel 32, and also that channel can be a 4-pole or a 6-pole or 7-pole according to their need. You don't need to make any changes or adjustments to the overall system. So I just also wanted to show you just an isometric view of the whole thing, because what we try to do here also, especially our system engineers, they wanted to do is a complete mirror image of the two chains. So that's also really helps to have a complete mirror image. And I was looking into some of the results were coming last week before I flew over from Australia, and the results were very, very spectacular. And as you can see, we also kept a corridor in between where you can essentially go in, like we kept a space for a person to move in and make changes to any make changes to any of the 3dB couplers here or the phases, so that if independently any channel wants to change their vertical component when they move on to ATSC 3.0, they can do that independently, don't need to modify any of the other systems. So this sort of system, what we found, This sort of system, what we found is usable for a US repack where you have a certain stage now, but before you go to a final ATSC 3.0 rollout, you have certain interim stages, and you can have the flexibility of adding or removing channels or swapping channels if needed. So just some photos, I just got it last night from our production area. So we already have done the single chain, and as you can see, so we are putting the second chain, which is work in progress. We're gonna be shipping it next week. And also, so there's our systems engineer manager who is showing, you can go in there and try to make any changes if needed to any chain. So just to conclude my talk, so we come up with generation 2.0 directional waveguide combiner. We essentially have doubled the peak power handling capacity. We have reduced the lead time when we can deliver compared to the previous one. And also, we simplified the installation. We call it a plug and play method, and during for any stage, interim or final stage, you should be able to make changes as necessary. And overall for ATSC 3.0, we say it's ATSC 3.0 ready. So that concludes my talk, and if you have any questions.